This summer, we joined Nanoworld Laboratories at the University of Cincinnati to research advanced battery technology. The lab is working to develop a lithium-sulfur fiber battery, which is flexible and can be worn and adapt to the human body. Compared to conventional lithium-ion batteries, the lithium-sulfur electrochemistry offers a high theoretical energy density, which would give the battery a long runtime, but sulfur is both non-conductive and brittle, making it a poor choice for a flexible battery. To address sulfur's limitations, UC Nanoworld uses sulfur-loaded carbon nanotube thread, which provides some flexibility, strength, and an increase in conductivity. Before a viable fiber battery can be created, the strength and conductivity of the cathode must be further increased. Our summer research objective was to assemble and characterize a hybrid cathode using carbon nanotubes which had higher tensile strength and electrical conductivity. The hybrid cathode is composed of a sulfur-loaded carbon nanotube thread and a densified carbon nanotube thread. To create the sulfur-loaded carbon nanotube thread, we spun vertically aligned carbon nanotube arrays into carbon nanotube threads, exposed the threads to oxygen plasma, and used a sulfur melting infiltration process to add the sulfur to the carbon nanotube thread. The other part of the hybrid thread is composed of a carbon nanotube thread which was exposed to acetone, creating a densified thread. This densified thread was combined with the sulfur-loaded thread to create our hybrid cathode.
To test the conductivity, the hybrid cathode was used in a coin cell battery and tested with electrochemical impedance spectroscopy. When compared to the original sulfur-loaded cathode, the resistance of our hybrid cathode was approximately 30 times smaller, making the hybrid cathode 30 times more conductive. A battery analyzer showed that our hybrid cathode also had capacity improvements at different discharge rates. We used a tensile tester to look at the tensile strength of each part of the hybrid cathode. We found the densified thread had a 1.4 times higher tensile strength than the original sulfur-loaded thread.
In the end, we were able to create a hybrid cathode that was both stronger and more conductive than the original sulfur-loaded cathode. This brings the research group one step closer to creating a lithium-sulfur fiber battery.
Fiber batteries would give product designers and electrical engineers the flexibility to innovate future wearable technology.
Based on our summer research, I plan to implement a 13-day unit with 11th grade Algebra 2 students. This unit will focus on optimal battery usage. The design challenge will have students create and refine a set of criteria for ideal battery consumption. The students will have opportunities to test and refine their criteria over several days of data collection. Afterwards, student groups will present their final battery usage criteria to the class.
I plan to implement a 13-day unit with 12th grade AP Physics 2 students. While our summer research focused on the start of new battery technology, this unit will focus on batteries at the end of their usable life cycle. Student groups will be given the challenge of designing a process to evaluate individual lithium-ion cells from recycled laptop and power tool batteries. The groups will have an opportunity to test and refine their battery evaluation process over several days. At the conclusion of the design process, student groups will present their final battery evaluation process, including test results and refinements along the way. As an extension, the students will use their tested lithium-ion cells to build a small battery pack which can charge a cell phone or any USB-powered device.